All right, so where do we go from here? Well, let's do one example. Okay, let's look at this extraterrestrial water example. It says that ionizing radiation inside the International Space Station causes water droplets to carry a charge. All right, so you have this radiation, and we're going to talk more about this later in the semester, but in space, there's radiation that comes from the sun and comes from gamma rays from, other stars and galaxies. And so you have that ionizing radiation will knock electrons off of various atoms, right? And that creates a net charge on that atom. So for that reason, you may have a water droplet that carries some sort of net charge. So let's say that I do have such a water droplet, okay? And that water droplet is some radius r, okay? We don't know what it is. But we do know that it has accumulated a net charge of 1 nanocoulomb, and there's 500 volts on the surface, all right? So my question is, what would be the radius of this droplet if it's a 500 volt potential at the surface and the net charge due to the ionizing radiation is 1 nanocoulombs? Well, we just use the one formula that we have. We know that the potential to anything that's like a sphere, right, that has spherical symmetry, like a point charge, and you can expand that out to something that's spherical like a water droplet, the potential due to the charge on that water droplet is going to be K Q over R. Simple as that. So at any distance r away from the center of this water droplet, you're going to get a voltage of KQ over R. But we don't want voltage. We already know the voltage at the surface, right? What we really want is the radius, right? And so that means if we just do a little switcheroo here, the radius is going to be KQ over V, right? If I put this in, my K, I know that that is 9 times 10 to the 9, okay? And my charge is 1 nanocoulomb, so that's 10 to the minus 9 coulombs. And the voltage is 500 volts. All right, so in case that's off screen, I'm just going to say it's 9 times 10 to the 9 times 10 to the minus 9 coulombs that has been accumulated on this water sphere, divided by the voltage at the surface, and we want the radius of that surface. And if I put all that into my calculator, I get an answer of 0.018 meters, and that's going to be equal to 1.8 centimeters. So this is one of those little, about 1 centimeter to 2 centimeter size water droplet that you would see in like those space movies that like leave and drift off in that low gravity space. Cool? Yep. So we're mastering voltage, all right? What do you think you do when you have more than one charge? Well, I'm going to tell you, you do the same exact thing we did for more than one charge when we're calculating potential, right? They're just going to add to each other. So in other words, the voltage, when you have more than one charge, is just the sum of all, the sum over I, is just the sum of all the little voltages, right? And I know that might look, it's like mathy, right? You got the summation sign of the I's and stuff. It just really means add up all the voltages. That's all it really means. And the cool thing, once again, voltage is a scalar, so we can just add them without worrying about any kind of angle, okay? So let's take this example that's on this slide. We have a 2 nanocoulomb charge, right? And we have a negative 1 nanocoulomb charge. And then, there's kind of like this little triangle here. Boom, boom. And we want to find out what is the net, right? The sum of the voltages right there. All you do is you add them. So V is going to be equal to, we'll say that this is V1 plus V2, which is going to be KQ1 over R. And that's going to be this R. And that R is 5 centimeters, right? And that's going to be plus KQ2 over R equals, and so this is going to be R1, this is R2. R2 is this distance right here. That's 4 centimeters. All right, and so now we can just put this in, right? So we have 9 times 10 to the 9 times 2 times 10 to the minus 9 nanocoulombs, right? All over 5 centimeters, that's 0.05 meters. Let's keep the SI units. All right? Plus 9 times 10 to the 9 times, this is negative 1 nanocoulomb, so I'm going to say negative 1 times 10 to the minus 9, all divided by now this distance here, which is 0.04 centimeters. And now I'm going to be able to find the net voltage at the spot due to both of those charges. If I add those all up together, I get a value of 135 volts. Check me if I'm wrong. Shoot me an email. Now, one thing I want to point out. I've been telling you up to now, don't worry about putting the signs for the charges. That's when you're dealing with vectors. Because when you're dealing with vectors, you've already taken into account the direction when you're setting up your free body diagram. All right? When you're setting up your vector picture. So in this case, you're just adding, you're just summing. So if you have a negative voltage, you just have to go ahead and sum that with your positive voltage, and that's going to be negative. So I want to make a distinction here. Don't worry about substituting the values of the charges if you're doing a vector addition, like with Coulomb's law, so forces, or electric field, which is another vector, because you've already picked the direction of the arrows in the various directions. All right. In the case of something that's a scalar, you are just like adding positives and negatives, right? So in this case, you will have to substitute the value of the negative charge, or just say that this instead of positive has to be negative because you know that that's a negative charge. All right. I hope that makes sense. Do more examples of these. There's so many problems of these in the book, in the homework on Khan Academy. And you're just going to see that this is the easiest version of any of the electric quantities that we've had to calculate so far. The reason why it's easy is because it's got the simplest form of the equation, right? It's just KQ over R. And there's no vectors, which is kind of cool. You don't have to worry about direction. You just have to worry about the distance.